Have you ever wondered how one of the best-kept secrets in naval engineering is built? A nuclear submarine. These vessels are capable of patrolling underwater for months undetected, powered by reactors that can operate for decades without recharging. But behind their power lies a design and manufacturing process so complex that it involves thousands of experts, millions of parts, and cutting-edge technologies. There are fewer than 150 nuclear submarines in operation worldwide. This small number is not due to a lack of interest, but to the enormous cost and complexity of their manufacture. Building just one of these vessels can easily exceed $3 billion, but a big question arises. How are these giant submarines, seemingly straight out of science fiction, actually manufactured? We will travel to the United Kingdom, to one of the most advanced shipyards in the world, specializing in bringing to life the colossi that silently patrol the depths. The history of submarines has much older roots than most people imagine. In the 17th century, Cornelis Drebbel, a Dutch inventor, amazed his time by building a rudimentary wooden device covered in leather in 1620 that could submerge several meters in the River Thames. Although primitive, it laid the foundation for a seemingly impossible dream: underwater travel. A few years later, in the midst of the American Revolutionary War, David Bushnell presented the Turtle, a small submarine designed to attack British vessels. His missions were unsuccessful, but the idea's military potential was demonstrated. As the decades passed, the advances of the Industrial Revolution gave rise to more ambitious designs, featuring steam propulsion and compressed air systems. Examples such as Robert Fulton's Nautilus and Narcisse Monturiol's Ictinio marked milestones in the 19th century. However, the real boom came in the 20th century, especially during the World Wars with the famous German U-boats, which revolutionized naval warfare thanks to their ability to operate secretly and attack without warning. Since then, submarines have become strategic assets for both defense and nuclear deterrence. Today, the incorporation of nuclear power has completely transformed the capabilities of submarines, taking them to levels of range and autonomy that seemed impossible just a few decades ago. Thanks to their state-of-the-art reactors, these vessels can operate for more than 25 years without refueling, giving them unique independence to patrol the oceans silently and with unparalleled endurance. This characteristic makes them true invisible guardians of the deep. However, achieving such a technological feat is not simple. The construction of a nuclear submarine is considered one of the most demanding and sophisticated processes in modern engineering. It is a task that requires thousands of parts assembled with absolute precision, the coordinated effort of specialists from multiple disciplines, and strict safety controls at every stage, from initial design to entry into service. In the United Kingdom, the Barrow-in-Furness shipyard is one of the world's epicenters for this technology. There, thousands of engineers, technicians, electricians, welders, and scientists work together to create vessels that meet the highest demands. Operating in secret, at depths thousands of meters, withstanding colossal pressures, and with no margin for error. In addition to its military importance, this shipyard is an economic engine for the region, providing thousands of direct and indirect jobs, and consolidating an industrial chain that involves suppliers from all over Europe. The construction of a nuclear submarine is not only a technological challenge, but also a national project. Design is the first major step and requires the involvement of more than 600 experts. It's not just a simple blueprint. A nuclear submarine can contain more than 1 million individual parts, nearly 400,000 kilometers of wiring, and more than 25,000 valves. It all begins on state-of-the-art computers, where the extreme conditions the vessel will be subjected to are simulated. This design process can take years before the first piece of steel even reaches the workshop. Construction begins with the reception of enormous steel plates, specially designed to withstand the enormous pressure exerted by the depths of the ocean. Each of these pieces, weighing several tons, is made of high-strength alloys capable of withstanding extreme conditions without deforming. Once at the shipyard, they are handled by powerful magnetic cranes that allow them to be moved with complete safety and precision. These plates then move to the cutting stations, where state-of-the-art plasma technology is used. This system allows for clean and precise cuts, with tolerances measured in millimeters, ensuring that each section fits perfectly into the final assembly. This level of detail not only ensures the watertightness of the hull, but also forms the basis for the strength and safety of the entire vessel, making it an essential step in the construction process of a nuclear submarine. The hull is divided into 8 main sections, each measuring up to 11 meters in diameter. After being assembled, these enormous pieces are transported, even on public roads, to the final assembly building, the Devonshire Dock Hall, a 200-meter-long structure considered one of the largest industrial facilities in the United Kingdom. There, beneath a monumental roof, the ship's final shape is taken. The sections are initially assembled vertically to facilitate internal access, and once completed, they are carefully rotated by specialized cranes that perform extremely delicate maneuvers. A mistake at this stage could ruin years of work. Inside, a submarine is a true technological labyrinth. Unlike a surface vessel, the internal space is optimized to the maximum, with 3 times more equipment than any traditional vessel. The heart of the vessel is, without a doubt, the nuclear reactor, accompanied by diesel engines and backup systems designed to ensure the crew's survival in any scenario. Stealth is the most critical feature. To minimize vibrations and noise, each component is mounted on high-tech damping systems. The result is submarines so quiet they've earned a reputation as the most discreet on the planet. The passive sonar is so sensitive that, under ideal conditions, it could detect a ship in New York from the shores of Southampton. The forward end of the ship, weighing about 270 tons, contains the main sonar, while the rear end, weighing about 230 tons, houses the propeller and rudder. Each of these parts moves slowly along the assembly line, advancing barely a meter per minute, under the watchful eye of engineers with decades of experience. The command deck, considered the true brain of the submarine, is built independently at the shipyard before being incorporated into the main hull. This module, approximately 22 meters long and weighing 180 tons, houses the vessel's most important systems. It houses the navigation controls, the sonar equipment responsible for detecting and analyzing the underwater environment, internal and external communications, and the systems for weapons control. Its design must be extremely precise, as any error could compromise the operability of the entire vessel. The captain's cabin is located above, providing the only individual space for the entire crew. From this vantage point, the commander has direct access to critical information and the tools necessary to make quick decisions in high-tension situations, making this section the submarine's operational command center. The second level includes the galley, a small dining area, and lounge areas. Although space is limited, amenities have improved over time. Crew members now have access to power outlets for personal devices, modern kitchens, and small details that make missions that can last weeks underwater more bearable. The sonar, a key component for navigation and detection, occupies a central space within the command deck, where data is processed and then sent to the control systems. Everything is designed to ensure fast and accurate internal communication. One of the most demanding tasks is welding the hull sections. Joining just 2 pieces can require more than 2 kilometers of welding. Workers perform this task in continuous shifts, in cramped spaces, and in temperatures that can exceed 130 degrees Celsius. It requires great skill and physical endurance, as a single error could compromise the safety of the entire ship. Each weld undergoes rigorous testing. Ultrasounds similar to those used in hospitals are used to inspect the interior of the joints, and mechanical tests are used to verify their strength. In many cases, the welds are even stronger than the hull steel itself. In addition, the shipyard has research teams that constantly test new materials and techniques to improve safety. Another key aspect is the external coating. The submarine is covered with more than 40,000 rubber tiles designed to absorb sound and make it virtually invisible to enemy radars. The assembly of all the internal systems is also a challenge. More than 1 million parts must be assembled by hand by a small team of specialized technicians. To ensure safety, cabins with monitors capable of detecting dangerous gases such as argon, which can be fatal in high concentrations, are installed. The Astute-class submarine, one of the most advanced submarines built at this shipyard, is equipped for offensive and defensive missions. Its torpedo chamber can accommodate Spearfish torpedoes with a range of over 65 kilometers and Tomahawk missiles, capable of hitting targets over 1,000 kilometers away. Before delivery, each submarine undergoes combat simulations where the crew trains in launch maneuvers, communications, and damage control. Everything must operate with absolute precision. The core of the ship is the nuclear reactor, a feat of engineering and secrecy. It runs on enriched uranium, which, when split in a chain reaction, releases heat to generate high-pressure steam. This steam drives turbines that produce the electricity needed for the entire propulsion and life support system. The reactor is being started gradually, reaching full power in about 2 weeks. Once operational, it can supply enough energy to power a city the size of Southampton. For safety reasons, the reactor's installation and activation are carried out by a highly specialized external team. This is one of the most secretive and closely controlled processes of the entire construction process. Once the submarine is fully assembled and ready for launch, a precise maneuver involving tugboats and shore-based equipment is planned. The transfer through narrow channels to the open sea requires impeccable coordination, taking into account factors such as tides, currents, and weather conditions. Once the submarine reaches deep waters, the final testing phase begins, in which each system is put to the test under realistic conditions. Navigation, stability, communication systems, and propulsion mechanisms are verified, ensuring that everything operates flawlessly. This procedure represents the culmination of years of design, assembly, and technical testing, and marks the point at which the vessel transitions from an industrial project to an operational asset of the Navy. Once this stage is complete, the submarine is ready to patrol the ocean depths for decades, moving silently and virtually undetectable, fulfilling strategic missions that depend on its exceptional stealth and endurance. Each nuclear submarine represents decades of research, thousands of hours of work, and the union of science, engineering, and military strategy. They are more than simple machines. They are symbols of silent power that patrol the depths, ready to act at any moment without the world noticing. Their construction is proof of how far technology can go when combined with the need to ensure security and deterrence in the world's seas.